Hi everyone, my name is Jia, PhD candidate in the University of Maryland, and today I'm excited to present BoolE, an approach for symbolic reasoning via Boolean equality saturation. Symbolic reasoning is a fundamental topic across the entire spectrum of the system design, from the chip design, synthesis, to the formal verification, and the hardware security. The functional symbolic reasoning has a profound application across various domains. In formal verification, it is essential for the task, like the identification of complex multipliers, as seen in the tool like the RevSCA. In the logic and data path synthesis, it enables advanced optimization and the efficient mapping of Boolean circuits. Furthermore, in the hardware security, the symbolic reasoning is fundamental for the Trojan detection. Although the symbolic reasoning is important, the existing state-of-the-art approach faces several challenges. The former method, like the WordRev and the commercial tool, the Jasper, while they can provide the soundness, they have the poor scalability issue and can be struggle when problem size increases. This method cannot be extended to the realistic size of the gate-level netlist. The machine learning or the AI-based method, including the Gamora tool, offer better scalability, but they often lack the formal soundness guarantees and can also be sensitive to the structure modification. It will impact the quality of results. On the other hand, the heuristic approaches, like the cut enumeration-based tool in ABC, has a poor quality of result, and they can be struggle after the technology mapping. All of the approaches cannot provide a strong balance between the mentioned metrics. Here, we provide a motivating example using a 3-bit bit-clustered host map CSA multiplier. A primary challenge is the obfuscation caused by the circuit transformation. During the synthesis and the optimization, the original high-level structure, like the adder and the carry chains, are often modified, fragmented, or entirely obscured. This makes it difficult for tools to recognize them. Considering in the small motivating example, the theoretically maximum of the number of the identifiable foreadder is 3. However, with the cut enumeration, it can only identify one foreadder in the node 49 to the node 50, and the another 2 foreadders is disappeared during the structure modification. The 2 disappeared foreadder cannot be recognized again without the netlist rewriting. Another key challenge lies in the reliance on the NPN classification. NPN will stand for the negation, permutation, and the negation. It groups the functions that are structurally similar, but not necessarily logically identical. While it is useful for some applications like the technology mapping, NPN classification doesn't guarantee exactness of the logical equivalence. This exactness problem is critical, especially for the tasks like the formal verification, where the precise functional matching is necessary. In this example, the single identified foreadder is an NPN foreadder. All of these challenges bring us to the BoolE, our novel approach centered around the Boolean equality saturation. BoolE is designed to provide formal guarantees for the exactness and the soundness in the symbolic reasoning. It leverages the term rewriting and the saturation technique. We have made several contributions to general equality saturation to enhance the scalability, including the rule set optimization and the parallelized extraction. Specifically, we targeted the identification of the data path functional unit. Our goal is to achieve a strong balance of the soundness, scalability, and the exactness. A core task in the symbolic reasoning is the functional unit identification. It involves detecting the elementary functional blocks, like the foreadders, the half-adders, and the entire adder tree within the gate-level netlist. All of these provide a critical word-level abstraction. This process is illustrated in this figure. The first step is finding the primitive XOR and the majority operation from the netlist. Then we pair this XOR and the majority roots that share common inputs. Finally, from these paired components, we can reconstruct the higher level structure. Ultimately, we can build the entire adder tree, providing a clear abstraction of the Boolean logic. BoolE is built on the principle of the equality saturation. This is a powerful rewriting technique that uses an E-graph or equivalence graph to efficiently represent and explore a vast space of functionally equivalent expressions. Rewriting rules are applied iteratively to this E-graph. This process continues until no new equivalence can be discovered, at which point the E-graph is considered as saturated. Here we provide an example of E-graph rewriting from the left to right through two separate rewriting rules. BoolE is a novel approach providing the formal guarantees for the exact symbolic reasoning. Its scalability is improved through domain-specific Boolean equality saturation and optimized extraction. It's designed to be agnostic to the structure variation, such like the situation introduced by the heavy logic reconstruction or the technology mapping. And we will demonstrate its efficiency with the end-to-end improvement in the real-world formal verification task. The rewriting rule set is crucial to the BoolE's power. This is divided into two main categories. The first rule set is the basic Boolean rule. We know that the structure variation obscures the original full adders, requiring the netlist rewriting to recover them by searching the expanded equivalent space. These Boolean rules are included the commutative, the associative, and the De Morgan's law to expand the E-graph for more equivalent expressions. For basic Boolean rules, we have the 68 of them. Second, building on the expanded E-graph, this rule then directly identifies as many XOR and the majority operations as possible, which are the building blocks of the adder. These rules are empirically collected from the 8 to 128 bits of the boots and the CSA multiplier. For the domain-specific rule, we have the 129 of them. A fundamental novel contribution of BoolE lies in its ability to handle the multi-input and the multi-output structure within the E-graph framework. The standard E-graph infrastructure often lacks the direct support for the multi-output operation. BoolE addressed this by introducing pseudo E-nodes. Here we create a pseudo full-adder E-node, and we use the first and the second pseudo operation to project its carry and sum outputs, respectively. The extraction of the full-adder, the first and the second E-node, is atomic, ensuring the structure integrity of the identified adder. The introduced pseudo E-node is theoretical sound and doesn't affect the quality of results. Our cost function is therefore defined to maximize the number of the pseudo full-adder E-nodes that can be constructed. The E-graph extraction process is guided by this algorithm. It employs a DAG-based cost extraction method, ensuring that the shared sub-expression can counted only once. This algorithm initializes a parallelized queue and calculates the cost based on their children. If a lower cost is found for a node, its cost will be updated, and its parents will be enqueued for re-evaluation. As we mentioned, the atomic co-extraction of the full-adder, the first and the second E-node, ensure the components are selected or deselected as an atomic unit. A challenge in the equality saturation, especially as the problem size increases, is that the extraction time can dominate the entire runtime. As we can show in this graph, sometimes the extraction takes more than the 95% of the total runtime. To mitigate this challenge, we have implemented the parallelized extraction. This involves processing the multiple elements from the queue simultaneously, performing the cost computation in parallel, and then deduplicating this result to minimize memory. This parallelized extraction can theoretically guarantee to provide the same quality of the result with the non-parallelized extraction. Further optimization in BoolE include an adaptive eGraph data implementation for memory efficiency. Additionally, we remove the redundant eNodes. We only retain one unique canonical representation per E-class to reduce the memory and the runtime. For our experiment setup, BoolE, which is built on the Egg framework, is released as open source. We use the CSA and the Boost encoded multiplier as benchmark, both with and without SAP 7nm technology mapping. Our baselines include the Descartes enumeration-based method in the census tool, ABC, and the state-of-the-art machine learning approaches, Gamora, which is the best paper of the DEC 2023. We also conducted an end-to-end case study on the formal verification, use RevSCA as the backend. Let's revisit the motivating example. During the BoolE's rewriting, the disappeared foreaddress is recovered, as illustrated in the blue node. Besides, all of the two identified foreaddress exact foreaddress, corresponding to the logical equivalent nodes. For the rewriting runtime, it takes 50 minutes for rewriting in the largest benchmark, and the scalability is way much better than the formal approach like the SMT and other commercial tools like the Jasper. For the formal verification, its timeout for the design larger than the 64 bits. Let's compare the result with the heuristic-based ABC and the AI-based Gamora. For pre-mapping benchmark, where the original structure is untouched, BoolE achieved the theoretical optimum for the foreadder identification in both of the CSA and the Boost multiplier. More significantly, in the post-mapping scenario, BoolE identifies an average of the 96 of the theoretical maximum in the CSA multiplier and 84% in the Boost multiplier. This result significantly outperforms than the two baseline, ABC and the Gamora. Besides, Gamora cannot provide the soundness. It can produce the false prediction in some time. To demonstrate the practical impact, we deployed BoolE before the formal verification process for highly optimized multiplier. The results are impressive. The left graph shows that BoolE consistently identifies more foreadders than ABC, especially as the bit width increases. The red figure illustrates the end-to-end runtime. Without BoolE, verification of this optimized multiplier timeout after 72 hours for designs larger than 24 bits. With BoolE, we were able to verify designs up to 128 bits. In the 24-bit case, BoolE provides a remarkable of 28 to 25-fold speedup in the verification runtime. This is all of the components of the BoolE I want to introduce. Thank you for your attention.